At the beginning of the chapter, I talked to you guys about Kc and Kp. I also told you there's other values of K we can use that we're going to learn about in future chapters. But what if we want to correlate between Kp and Kc? Easiest thing to do is memorize this equation. I'm going to show you how to derive the equation. You are not responsible for deriving this equation for my class. But some people work better with understanding where the equations came from, so I will go ahead and derive it. If you don't want to derive it, ignore that part and just work through the examples. But you should be able to use this conversion at any point to convert between Kp and Kc. So let's go ahead and look at the specifics. As a reminder, let's look at this equation here, SO2Cl2 in equilibrium with SO2 and Cl2. Everything is in the gas phase, so this is a homogeneous system. If I want to write Kc for this expression, or the Kc expression for this equation, I'm going to write products over reactants. So the concentration of SO2 times concentration of Cl2 divided by the concentration of SO2 Cl2. If I was to write Kp, remember P is the partial pressures of each species at equilibrium. And I forgot to specify that, but these are written, we don't have to specify in the equation, these are equilibrium. It's implied because I have Kc, so it has to be equilibrium concentrations. For Kp, it has to be partial pressures at equilibrium. You can ignore the little dash there in the title. This should just say Kp. If I was to look at Kp, though, it would be the partial pressure of SO2 at equilibrium times the pressure of Cl2 at equilibrium divided by the partial pressure of SO2 Cl2 at equilibrium. Now, I know I already told you there's a relationship between these two. It's an equation. You can memorize the equation if you would like, and it is Kp is equal to Kc times RT times the change in N. I just haven't defined what change in N is yet. But first, before I do that, I want to go ahead and derive this relationship. So I've got Kc, I've got Kp. We hopefully remember from first semester your ideal gas law. The ideal gas law shows us that PV equals nRT. We can also look at this specifically to one, brain is tired, specifically to one species in a reaction. So if you remember from Dalton's law of partial pressures, we could talk about the partial pressure of a system. So we could say, let's just say P of X. So any species we're looking at, we'll just define as X. P of X times V equals N of X RT, or it's the partial pressure of just that species times the volume of the system equals the moles of that species times R times T. We can also rearrange this equation and say P of X is equal to N of X over V times RT, and hopefully you recognize that this is just molarity. So we can say P of X equals the concentration of X times RT. And hopefully this also looks familiar because this is very similar to your osmotic pressure equation if I was equal to 1. So we're going to take advantage of this. And we're going to substitute that into our equation. We know that the pressure of X is equal to the concentration of X times RT, times the gas constant, times the temperature of the system at that point. I'm going to substitute this portion into this equation for P sub X. So let me go ahead and write that up here. Kp is equal to the concentration of SO2 times RT times the concentration of Cl2 times RT divided by the concentration of SO2 Cl2 times RT. I forgot to put the brackets in there properly. That should be brackets, because those brackets, again, mean concentration. All of these are divided times RT. Now, if you look at this equation specifically, we could say, okay, well, 1 RT is canceling with 1 RT. That's giving me Kp is equal to the concentration of SO2 times Cl2 times RT divided by SO2 Cl2. And I'm going to actually pull that RT completely out and say this. It means the same exact thing. It's this fraction, this ratio times RT. But that ratio is the same as Kc. So Kp is equal to Kc times RT. Now where do I get that change in N thing? The change in N, and if you don't trust me, you can do the same derivation with other systems where the ratios are different. The change in N is the change in the number of moles I have between the products to the reactants. So products minus reactants. This system was 1, 1, 1. I went from 2 moles to 1 mole. So my change in N, change is always final minus initial. I have 2 moles minus 1 mole. Overall gives me an answer of 1 here. The equation, Kp equals Kc times RT raised to the change in N. Here, for this specific example, Kp equals Kc times RT raised to a 1. And these are parentheses around here. Let me write that so you can actually read it the way I meant it to be. Kc times RT raised to a 1. And I can ignore it for this reaction specifically. And that's how I get Kc times RT. But in general, I want you to remember that it's always raised to that change in N because the number of moles. And it's always your products minus your reactants. That change in symbol means final minus initial. So and if you don't believe me, you can go ahead and do the same derivation for every one of these examples and you're going to see that the answers come out the same. But for simplicity's sake, let's go ahead and just work these out quick using our equation Kp equals Kc times the product of RT raised to the change in N. And I'm not going to solve the answer out here because I don't have a Kc value for these, but you could if you wanted to and if you needed to. You can always convert between Kp and Kc and you should be comfortable with those conversions. For the first reaction, H2 gas plus I2 gas going to 2HI. If I was to write Kc for this, I would write concentration of HI squared over concentration of H2 times concentration of I2. If I was to write Kp, I would write partial pressure of HI squared divided by the partial pressure of H2 times the partial pressure of I2. For this, though, when I want to convert between the two, for Kp to Kc, I look at the change in number of moles. I have 2 moles here, I have 1 and 2 moles here. So my change in N is 2 minus 2, which is equal to 0. Kp equals Kc times RT raised to 0. Anytime something is raised to a 0, it goes to 1. So here, my Kp is equal to my Kc. So no matter what value I had for Kc, that would be the same value for Kp. What about the second example? 2 moles of NO2Cl are in equilibrium with 2 moles of NO and 1 mole of Cl2. Change in N here. I have 2 and 1, so 3 minus 2 gives me a 1. Kp equals Kc times RT raised to the 1. Kp equals Kc times RT. And remember R, your gas constant, 0.08206 liter atmosphere per mole K. You can convert to other units if you remember the conversions between atmosphere and torr, atmosphere and pascals, atmosphere kilopascals, atmosphere millimeters of mercury. You can convert to the other versions of R. What about the next example? What is my change in number of moles here? I have 2 moles of NH3 in my product I have 1 plus 3, 4 moles between the N2 and H2 in my reactants. So overall, -2. Kp equals Kc times RT raised to the -2. Yes, that is valid. NH4Cl in equilibrium with NH3 and HCl. Don't let this one trip you up. Don't get too comfortable. This is a solid, which means it does not interact in our equilibrium expression. Solids stay relatively constant in the overall reaction, so it's not participating. So here, my change in the number of moles, and I don't remember if I specified this or not, but change in number of moles is number of gas moles. So here I have 2 moles of product, 0 moles of gas for reactant, gives me an overall 2. So Kp equals Kc times RT squared. And the last example, H2S gas plus NH3 gas in equilibrium with NH4HS solid. This is also a solid, so it's not going to behave in our expression. Change in N is 0 minus 2. I don't have any moles of gas in my product. I have 2 moles of gas in my reactants. Gives me an overall -2. Kp equals Kc times RT squared. Now again, I recommend you practice some of these. Even if you just make up some numbers. You know, let's say that the H2 plus I2 giving in equilibrium with H2I has a Kc value of 100 at 1 random degree or 1 random temperature, then we know what Kp would be. I recommend doing that with all of these though, practicing through these, and also practice through the other module where we actually looked at manipulating the equations, reversing them, multiplying them, inverting them, whatever different variations you can do. Practice that because you're going to see that in examples and you're going to get tripped up, and I don't want you guys to get tripped up. So work these examples, remember this equation, and start doing the math until you're comfortable with it.